data 3.1.
Guys, we are not using our book anymore for notes.
Sayonara book.
Sayonara book. We're going to be using that packet of notes that you got in class today, so make sure that you have that. If not, stop the video and go onto Student View and print off your own copy.
Yep.
Or get out a sheet of paper and write it all down. All right.
Got it.
Our objective today
Blah, blah, blah.
is
One of those.
to determine if data is linear and proportional based on the rate of change.
Okay, let's do this.
Okay. What's happening to it?
I don't know.
Okay.
It's not working.
There it goes. Okay.
Now we'll do this.
So first, we have a real-world link. Marcus can download 2 songs from the internet each minute. That's kind of slow. Is that slow? Yeah. This
2010.
That's true. This is shown in the table below. So you can see that we have time in minutes as our X value and number of songs as our Y value. So we forgot to turn off the dinging.
I know. That's right.
It's okay. So anyways, we have time in minutes going up by 1. It's 0 minutes, and he can download 0 songs, obviously. In 1 minute, he can download 2 songs, and so on and so forth. So what we're going to do here in number 1 is we're going to compare the change in the number of songs, which is Y, to the change in time, and we're going to call that a rate of change. Now, one thing you need to know is you're always going to put your Y value on top as a ratio,
okay,
and then your X value change goes on the bottom.
So what is it called? Greek change in, it's a triangle.
Delta Y.
Yep. Over.
Delta X.
So change in Y over change in X. Okay.
So how is Y changing? Well, it's increasing by 2 every time.
Right here, plus 2.
And it does that every single time, right? It's not like it changes.
2 to 4, 4 to 6, 6 to 8. Yeah.
It goes by 2s. And then change in X on my X column, or I guess it's my row, it goes up by 1. So we would say that our rate of change is 2 over 1 or 2, or in words we would say the number of songs increases by 1 or by 2 for every minute.
Number of songs increases by 1.
2.
Oh yeah.
Yeah, I messed it up first.
And song
per minute.
Per minute. There we go.
Cool.
It's really small.
Okay, now we're going to graph it on this graph. Now, there are some big empty boxes here that we need to put in first. So, hopefully from science you remember independent variables. If not, we're going to tell you. The X is always your independent variable.
Yep.
It can stand on its own 2 feet. It can just stand there by itself.
Right.
All right, so we are going to put time in minutes in our X axis.
So you can say time, and then you can do parentheses minutes, or you can write time in minutes. Either one. Okay.
And then your Y values is the number of songs.
Okay.
Oh. You're really talented.
Holla!
I was sideways. She was literally writing this way when I was going here. Okay, so then all we got to do is pop those dots on our graph. So our first one is 0, 0. So we're going to
right here.
Yep, right where the zeros can connect. And then we're going to do 1, 2, so over to 1, up to. Hopefully you remember graphing from 7th grade too. I'm staring at my computer screen and not at you guys, sorry. And then over to up 4.
So over to time, and then up to 4 songs.
And then 4, no, yeah. No, it'd be, yeah, 4, no, 3, good grief, Richardson. 3, 6, and 4, 8. So, our lines are showing a constant rate of change by increasing the same amount every time, and it makes a straight line. I guess I meant our dots. So there's 2 ways to look at it. At the graph, which shows a straight line, or at the table, which shows an increase of the same amount every time.
Right. So do you want me to connect these? I don't think we do.
No connecting of the dots.
Because we're very specific. We're saying at 0 minutes we have 0 songs. At 1 minute we have 2 songs. So there's no in between on this one. So that's why we don't connect it.
Right.
Okay.
Okay.
So graph it. There we go.
We did.
Oh, then describe the pattern shown on the graph.
Oh, it is a straight line. It appears to make a line.
Oh, that's the pattern.
That's the pattern. Yeah, we talked about it. So
okay,
it makes a line. All right. So again, what we just showed you. These are called linear relationships because they make a line. So in a graph, it is shown by a straight line, either up or down, or straight across, or straight. It just is a straight line.
Right.
And in a table, how is it shown?
Oh, sorry.
In a table, how do we see constant rate? How do we see a linear relationship in a table?
Okay, hang on. Is this backwards?
No, we're just going. This is the key concept.
Okay, hang on.
Guys, we were really confused
Yeah.
just a minute there.
Yeah.
Look at this table. It's totally flip-flopped. You should never do that, ever.
Yeah, I don't know why this book did this.
But anyways.
We didn't make the book, all right?
Somebody
Right.
would have been better.
Yeah.
Anyways, no offense. Okay, so anyways, this is flipped upside down. It's the same table, but
That's what
anyways.
got me.
So what we're saying is linear relationships are shown in a graph by having a straight line, and linear relationships are shown in a table by
having a constant rate of change.
right, which is shown on this page, and we'll keep going.
So up by 2, up by 2. That's constantly up by 2.
Or down by 4, whatever it is. All right, so here's an example, and you have this in your notes. So we're going to go through and look and see, is this relationship linear? If so, what is the constant rate of change? So is it linear, yes or no, and then we'll find the constant rate of change. Actually, we have to find the rate of change first and then decide if it's linear. So I can see that we're doing the number of transactions and the account balance. So after 3 transactions in some kind of an account, I have $170.
Right.
Okay. Then at 6 transactions, it looks like it's going up 3, but my account balance is decreasing. And that's okay. You can have a decreasing balance. Well, you really don't want to, but that's okay.
Right.
But you can have a decreasing table. So this goes down by 30. And then on the other side, again, it's going up by 3 each time. So it goes 3, 6, 9, 12. You're looking for that pattern. And then on the other side, we're going down by 30 every single time. So our constant rate of change would be -30. Remember, we do delta y over delta x. Maybe we should indicate that this is y and this is x too.
Okay.
So our number of transactions is x and our account balance is y. So delta y, or change in y, is -30.
So that's here.
And then our change in x was +3 or just 3. So you can say this, it goes down $30 for every 3 transactions, or better yet, down $10 for every transaction. So every time they go to the bank, they're taking out $10. So our constant rate of change is -10/1. And would that indicate that it's linear? Yes, it is.
Yes.
Because there is a constant rate of change.
And so notice what Rich did here. She relayed this to a real world problem. It's going down by $10 every transaction.
That's what's called interpreting the rate of change, or interpreting the slope, which we'll talk about in several more lessons.
So you're just making it real.
Making it real.
Got it.
All right, so let's try these. Would you go ahead and try these? Look at your x and your y and see if you can come up with a constant rate of change. If there is one, it will be linear. If not, it's not linear.
So x and y are not labeled, but x always comes first and then y follows.
And then on your graph, again, look back a couple pages. If it makes a straight line, it's linear, but then you have to find the rate of change. Go ahead and pause now.
Okay, hopefully we were able to solve this. We looked at the change in y first. So going from 95 to 90, we had a decrease of 5. Going from 5 to 10, it was an increase of 5. We reduced that down, we have -1/1. So we were able to see that, no, this is not a constant rate of change.
Nope, it's not.
Nope.
Because we couldn't see.
Yep, because we didn't squint hard enough.
Okay, then this goes
So,
90.
But this is a great example, because right here, if you just look at the first one, sure, done, I got it.
Yeah, but we didn't. And now look at what happened. We totally got it wrong.
Right.
Because 90 down to 86 is down 4.
Mm-hmm.
And then 86 down to 82 is down 4. So this is not a constant rate of change because it does not follow the same pattern every single time. So, no. Now, in our graph, it is a constant rate of change because it is a line, and the rate of change is going down 20 for every 4 volunteers.
Mm-hmm.
Okay.
Yeah.
No, every 8 volunteers.
Oh yeah, it's right there. Okay.
Okay. All right. So now we're talking about proportional linear relationships. If linear relationships are in fact linear, meaning that they make a straight line or have a constant rate of change, they are proportional if, if they have a constant ratio as well as the constant rate of change. What we're looking at is we're going to compare several different values in a table or in a graph and see if we get the same thing. So let's look at what it looks like before.
Okay.
Before we make it too hard.
So here's, you can come back.
You can come back to this. It'll make more sense once we do it. Okay. So the first, use the table to determine if there is a proportional linear relationship between the temperature in degrees Fahrenheit and temperature in degrees Celsius, and explain. So the first thing we're going to do is decide, is it linear, by seeing if it has a constant rate of change.
Okay.
So we're going to, again, degrees Celsius is X, and our degrees Fahrenheit is Y, and we're going to do change in Y over change in X, and then I'm going to draw my little arrows on my table and see what our change is. So X looks like it's increasing 5 every single time.
5 to 10, yep.
And we're going all the way
doing this.
We're going all the way through that table.
You got it.
All right, and then on the bottom, it looks like it increases by 9.
Yep, that's 9 again. 9 again.
9 again.
9 again.
So our change in Y is 9. So that's my
Change in
numerator.
Y, 9.
And then change in X, 5. Now, I can't reduce that. So I just leave it like that. Just leave it straight up and down just like that. Okay, so does it have a constant rate of change? Yes, so this is linear, so we would write yes. Now, is it proportional? It tells us to determine if they are proportional by looking at a table. Choose 3 columns and compare the ratios. So we're going to do 32 over 0. And we're going to write the Y on top. We'll do the 3, I guess. So 32 over 0. And we're going to compare the decimal answer to that to 50 over 10.
Is that there? Oh.
Yeah, just 3 columns.
Okay. 50 over 10. Okay.
And then we'll do 68 over 20. That's fine. You can do any 3 you want. I just popped them out. Okay, so if I divide these out, the first one is going to give me, well, 32 divided by 0, you can't divide by 0. Only Chuck Norris can divide by 0. So this is undefined. And if you try to do that in your calculator, it's going to say error. Means.
And I think it even says like divide by 0 error.
Yeah, so no go.
Okay, why is the calculator's not working?
Okay, well, I know that 50 divided by 10 is 5.
Yep, because those zeros just cancel.
And then 68 divided by 20 is 3 point something.
Okay.
3 point... it's
something.
It really doesn't even matter because I already know.
The first 2 weren't.
The first 2 did not give me the same decimal answer when I simplified them. So that means this is not proportional.
Okay, so let me get this straight. One can be linear. It can be linear and not proportional?
Correct.
Okay.
Now, if you go to the next slide, this is what it might look like on a graph.
Okay.
So we're going to look and see, does it have a constant rate of change? Is it making a line?
Yes.
Okay, so then this data is linear because it has a constant rate of change, or it makes a straight line, either way.
Okay.
Constant rate of change. Now, okay, so it's linear, but is this data proportional? Looking at a graph, if it does not start at 0, it is not proportional. This graph does not begin at 0. It begins at 0.32, which is basically just a graph of what we just talked about in the previous table. So this is not because it does not start at 0. It's easy as, there's no math involved.
Just that simple?
Yeah.
So it's proportional if it starts at 0, not proportional
if it doesn't start at 0. So like there's really no math. You're not doing math. You're just looking at graphs, which is pretty much math. Okay. Okay, so again, you try this one on for size. Weight is going to be X. Mass is going to be Y.
Okay.
You're going to do change in X over change in Y. Compare 3 different ratios.
Change in Y over change
I'm sorry, change in Y over change in X.
So and you're going to find linear first.
Yep, find linear, and then decide if it's proportional. If it starts at 0, 0, it is. If it doesn't, it's not.
Okay.
So this one, it doesn't have a 0 anywhere, so we don't know if it's proportional or not just by looking at the table. You have to compare the 3 columns like we did in the previous example. Go ahead and try it out.
All right, so we looked at this table. We found the change in X, which was plus 20 each time. We found the change in Y, which was plus 9 each time. And we identified that on our graph, or our table, excuse me.
Then we put that in our ratio here of change in Y over change in X, 9 over 20, so yes, it is linear.
So leave it as a fraction. Leave it just like this. Don't make it a mixed number. Don't make it a decimal. Leave it here.
Now, to decide if it's proportional, we compared 3 different ratios within our table, divided them out to find the decimal, equivalent of that or compared them by finding the decimal, and each one of them equaled 0.45. So we know that this is, yes, proportional. So
You got it.
if I were to make a graph, it would start